So, today we are going to continue with some more problems related to convolutional code. So, let us solve some more problems and then we will move to our other topic. So, first question is on feed forward encoder inverse. So, what is encoder inverse? We will talk in a minute. So, many a times we are interested in estimating the information sequence directly from the receive sequence without decoding it. So, for example, if you are encoding a sequence using systematic encoder, then you can directly from the receive bits you can get back your information bits. However, if you are using a non-systematic encoder, then you cannot directly get the information bits. So, we are talking about an encoder inverse, which will allow us to recover back the information bits directly without decoding. So, in this problem we will look into what is an encoder inverse and under what condition the encoder inverse exists. So, as we know that our coded bits can be written as our information bits times this generator matrix, encoding matrix, and the problem that we are looking at is finding out the encoder inverse, and we will talk about whether a feed forward inverse for this encoding matrix exists or not and under what condition it exists. So, if there exists a feed forward inverse, then if we from the receive sequence, if we just multiply by the encoder inverse, we can get back our original information bits without decoding after some delay. So, this d l is some delay d l. So, what we are saying is we are interested in finding this encoder inverse. Does this encoder inverse exist? A feed forward encoder inverse, does it exist such that GD inverse is some delay element, and what is the use of this? So, if you have your information sequence VD, if it passes through this encoder inverse circuit, we can directly get back our information sequence. And in many cases, for example, if the channel conditions are good, you may directly want to first guess or check whether the information bits are directly estimate information bits. So, you may want to pass it through this encoder inverse circuit. So, I am now stating without proof the condition under which these encoder inverse exist, a feed forward encoder inverse exists. So, for a rate 1 by n code, a feed forward inverse will exist if the greatest common divisor between these n generator sequences of this rate 1 by n code, if the greatest common divisor among these generator is some delay element, this L is something which is greater than or equal to 0. So, they do not have any term common in them, just some d times basically some delay element. So, we do not want these generator sequences to have any term common between them. If they have any term common between them, then a feed forward inverse would not exist, then there will be a feedback inverse. Similarly, for a rate k by n code, a feed forward inverse will exist if and only if the greatest common divisor, if you look at set of all determinants of k cross k sub matrices of this generator matrix, then the GCD of the set of determinants should be again some d raised to power L, where L is a positive number. So, we do not want the determinants of this k cross k, all possible k cross k submatrices to have any common term among them. If this condition is satisfied, a feed forward inverse exists. So, let us take an example where feed forward inverse exists. So, we are considering a feed forward rate 1 by 2, this is a rate 1 by 2 encoder. So, G0D is this one and G1D is this. And what is the common divisor between them? We can check, basically they do not have any common terms. So, the greatest common divisor is 1. So, if we go back and look at our condition for encoder inverse to exist, this condition is satisfied. So, for this particular code with GD given by this, will have a feed forward encoder inverse, and in this particular case the feed forward inverse is given by this. Okay. So, you can check GD inverse will be 1. So, you can just do a simple check, 1 plus d square plus d cube into 1 plus d square plus 1 plus d square plus d cube into d plus d square. This is, so this is 1 plus d square plus d cube plus d times d cube plus d4 plus d square times d4 plus d5, and then multiply this with this, we get plus d times d square plus d cube plus d4 plus d square plus d cube plus d4 plus d5. Okay. And let us see. So, d5 cancels out, d4 cancels out, then this d4 cancels out, d3 cancels out, d2 cancels out, d cancels out, d3 cancels out, d2 cancels out. So, what we are left is basically 1. Okay. So, and you can see this is a feed forward inverse. So, if you have your VD and if you pass it through this thing, what you will get is your get back your information sequence. Okay. Get back your information sequence. Now, let us look at example for rate r equal to 2 by 3. So, in this case we first have to find the determinant of all 2 cross 2 submatrices. So, what are those 2 cross 2 submatrices? One of them is this 1 plus d 1, next one is 1 plus d 1 plus d 1, and the third one is d1 1 plus d 1. So, these are the 3 2 cross 2 sub matrices, and we can find out the determinant in this case. In this case, it's, let us call it A, B and C. In case of A, the determinant is 1 plus d square. In case of B, the determinant is 1 plus d square. So, that is 1 plus d square, and C is d plus 1 plus d. So, that is 1. So, these are the determinants of these 2 cross 2 sub matrices, and that is what I have listed here, 1 plus d square, 1 plus d square and 1. Now, we need to check what is the greatest common divisor among them, and in this case the greatest common divisor is again 1. So, they do not have these determinants of these 2 cross 2 sub matrices do not have any term common among them. So, in this case also a feed forward inverse exists, and this is given by this. Okay. And again we can check that GD inverse is basically will be some delay elements where L is greater than equal to 0, it will be something like this. We can verify this quickly. Let us see, this will be 1 plus D times 0, and then this will be D 1 plus D. So, this is 2 cross 3, and this will be 3 cross 2 matrix. So, what we will get is a 2 cross 2 matrix, and so this will be some I times 2 cross 2 matrix. So, let us just work out. So, this will be 1 plus D times 0, that is 0, and then you have D times 1, and this is 1 plus D. So, that is 1, first term will be 1, and then this will be multiply this by this. So, that is 1 plus D into 0, that is 0, D into 1 plus D. So, that would be D plus D square, and then 1 plus D into D. So, that is again D plus D square. So, this will be 0. Next, multiply this row by this column. So, what we get D times 0, 1 times 1, 1 times 1. So, that is 1 plus 1 is 0, and if you multiply this by this, the second row by second column, what you get is 0 times D, 1 times 1 plus D, and 1 time D. So, that is 1 plus D plus D. So, that is 1. So, again what we are getting for this case is GD inverse is a identity matrix. So, L is 0 essentially here. Okay. So, this is a inverse for this generator matrix, and we can see that this all the terms are feed forward terms, is 1 by D and 1 1. So, this is a feed forward inverse for this convolutional code with this generator matrix. Okay. So, now we to recap basically. So, the condition under which the feed forward inverse of a convolutional code whose generator matrix is given by GD is given by this condition for rate 1 by n code, and for a k cross n code it is given by this condition. Now, catastrophic encoders do not have a feed forward inverse. So, for a catastrophic encoder, we will just show you that their inverse has feed back terms. So, let us look at one example. So, let us consider a convolutional code whose generator matrix is given by this. So, this is a rate 1 by 2 convolutional code, and it has 4 states because the maximum degree of D is 2. So, the generator sequence is G0D is given by 1 plus D, and G1D is given by 1 plus D square. Now, first thing that we check is what is the greatest common divisor among G0 and G1. As it turned out, in this case the greatest common divisor is 1 plus D. So, that is not same as D to the power L for some L greater than 0. So, that means for this generator matrix, we do not have any feed forward encoder inverse. So, there does not exist any feed forward inverse for this particular convolutional code with generator matrix given by this. So, let us take an example of u of d given by 1 by 1 plus d. This is a typo, this is 1 by d. Now, 1 by d can be written as 1 plus d square plus d cube. So, this is an all one sequence. So, our input is all one sequence, which can be written as, in this d notation, it can be written like this. This is my u of d. Now, if I give this input to my convolutional code, whose GD is given by this, what is my output? My output is UD times GD. So, this will be given by this. So, note my input has infinite weight, but the output only has weight 3, and this is precisely an example of a catastrophic encoder. So, you can see my input has infinite weight, but my output has finite weight. So, catastrophic encoder would not have a feed forward inverse, as this condition is violated. Next, we look at a class of rate 1/2 non-systematic encoders. So, we are looking at a rate 1/2 non-systematic feed forward encoders whose generator matrix is given by this, and these generators G0D and G1D satisfy this property. So, what is this property? It says G0D plus some delay, that is beta is greater than equal to 0. So, some delay of G1D is given by d alpha, where alpha is also something greater than 0. Okay. Now, just take a simplified case. I mean, let us say alpha is 0, beta is 0. So, what does it say? It says G0D plus G1D is 1. So, then I can essentially, looking at these generators, I can essentially find out that this encoder has a very simple encoder inverse. So, which is just 1 and 1, if alpha is this. So, these are known as quick look in encoders. Why they are called quick look in encoder? Because quickly looking at this encoder, you can actually easily find the encoder inverse, and essentially encoder inverse just consists of 2 taps. So, in some sense, for a systematic encoder, the inverse is of form 1 and 0 for a rate 1 by 2 code, and here they are of the form 1 and d beta. So, they are in some sense closest to systematic code, if you want like to call them. So, this quick looking encoders have a very simple encoder inverse, a feed forward encoder inverse, and that is given by this. And you can verify that GD inverse is your d times alpha. Okay. Now, note that the encoder inverse of quick looking encoder has just 2 taps, 1 and this d beta, and it has a feed forward inverse. So, this cannot be a catastrophic encoder. We just showed in the previous slide that a catastrophic encoder does not have a feed forward inverse, and since this has a feed forward inverse, this cannot be a catastrophic encoder. So, because they have a feed forward inverse, they are not catastrophic. And as I said, you can very easily recover back your information sequence by making your coded sequence pass through this encoder inverse. So, if your output sequence is given by VD, which is this, then once VD passes through this encoder inverse in encoder inverse, what we get is V0D plus d beta V1D. Now, we know that quick looking code have this property that G0D plus beta G1D is d alpha, and V0D is this is equal to G0D times UD. Similarly, this one is G1D times UD. So, from this condition and from here, this will come out to be d alpha times UD. So, among the class of non-systematic encoders, quick looking encoders have a very simple encoder inverse circuit, and one can easily find out what the information bits are from the coded bit without decoding. The next problem that we are going to talk about is about a distance measure for convolutional code. So, we will first define what we mean by column distance function. As we know, a convolutional encoder can continuously encode an information sequence. So, we can have an infinite length input sequence and correspondingly an output sequence. Now, we define the column distance function for a convolutional code as follows. So, before that, I am describing output code sequence V, which is truncated to up to length L. So, this notation that you see V sub L, it shows essentially our code word up to time L. And what is our code word up to time L? So, this will be V0, V1, Vn minus 1, then V1, Vn, because it is a rate, this is a rate, let us say this is a rate 1 by n code, then this is for first time instance you have n bits, second time instance you have n bits, and then for L time instance you will have n bits. So, this is your truncated code word up to time L. Similarly, I can define my truncated information sequence. Okay. So, just a minute, this is a typo, this should be k minus 1, this should be k minus 1, k minus 1, and of course, if k is 1, there will be just one input. So, you have for first time instance you have k inputs, second time instance you have k input, and similarly for L time instance you have k input. Now, note that both your information and coded sequences truncated up to length L. Now, we define column distance function of order L as follows. It is the minimum distance between two truncated code words of length L, such that, so you can see it is the minimum distance between two code words V1 hat and V1 double hat, both of length L, such that U dash and U double dash, they are not same. So, it is essentially Hamming distance between two truncated code sequences. Now, we know that Hamming distance between two sequences, minimum distance can be written as minimum weight of a non-zero code word. So, the same thing we can write as minimum weight of a Lth truncated code word belonging to a non-zero information sequence. So, we can define our column distance function of order L as minimum weight of Lth truncated code sequence belonging to a non-zero information sequence. Now, the thing that you have been asked to prove here is show that as L goes to infinity, this column distance function tends towards free distance of the convolutional code. In fact, after 3 or 4 constraint length, you will see the distance reaches d free and then it remains there, column distance function. So, by definition, what is a free distance of a convolutional code? It is the minimum weight path that has diverged from an all 0 state and merged back into all 0 state. How do we find minimum weight code word, minimum length code word? So, if you have a convolutional code without loss of generality, let us say we are transmitting all 0 code word, then minimum weight code word will be the length of the minimum weight along all non-zero, a path that goes through non-zero state. So, let us say you have some convolutional encoder, some 4-state convolutional encoder, and this is let us say your all 0 state, all 0 state. So, all 0 state, and let us say you have some diversion from this and then you coming back. So, this is your all 0 state, and what is your column distance function? It is a minimum weight of your code word belonging to non-zero information sequence. And what are the paths through the trellis diagram? These are all our valid code words. So, we need to find a path through the trellis which has minimum weight. So, and that would be our free distance. So, it's the free distance is minimum weight path that has diverged from all 0 state and merged back, right. So, that to get a non-zero weight, you essentially diverge from all 0 state and then emerge back to all 0 state. Now, let us assume that at time t equal to j, so Vj represents the shortest re-emerge path through this trellis diagram or straight diagram, which has weight of d free. So, if t equal to j is the smallest time which represent the shortest re-emerge path through this trellis diagram, then what does it mean? It means if we denote by dl the minimum weight of all re-merged path. What is re-merged path? So, these paths which are diverging from all 0 state and then merging back into all 0 state. These are our re-merged path. Now, what we are saying is for t equal to j, that is the smallest re-emerged path which has weight equal to d free. So, if you have any time any j which is greater than any time which is greater than this j, then your column distance column function will be equal to the free distance. Why this is so? Because we have said that for time equal to j, that is the shortest re-emerge path through this trellis diagram, which has free distance, which has weight equal to free distance. So, if we take any time larger than that, then of course, we will have a re-emerge path having minimum distance please d free. Now, if there are any non-merged path, what are non-merged path? So, these paths which are diverged from all 0 state, but have not yet merged to all 0 state. So, those are unmerged path. Now, for a non-catastrophic encoder, any path that is not merged must accumulate weight. It is only for the catastrophic encoder we have situation where input weight is higher and output weight is smaller, but if it is a non-catastrophic encoder, it will accumulate weight. So, if we have a non-systematic encoder, any path which has not yet merged with all 0 state will try to accumulate more and more weight. So, what is going to happen? So, if we look at distance for column distance for unmerged path, then as L tends to infinity, this distance will also grow, this also go to infinity, because it is a non-catastrophic encoder. So, what we have shown is, so for L greater than j, for all demerged path, this column distance function is d free, and for unmerged path, this is going to be infinity as L goes to infinity. Hence, we can say that limit dl is minimum of the column distance for remerged path or unmerged path. This is infinity, this is d free. So, we know that as L tends to infinity, the column distance function will be d free. So, this proves that column distance function will go to d free as L goes to infinity. Thank you.